with this question. So suppose you have such a thing. So what can X be? So that's the question.
Is it like sub-Gaussian?
Huh?
Is it sub-Gaussian, like excess sub-Gaussian?
Well, yeah. So the definition of sub-Gaussian just requires something like this. But yeah, so I wrote in the homework. So that's a typo that I put a absolute value on it. Suppose I put the absolute value. What?
Piyush, are you saying
Sorry?
something? I can't hear you.
Huh? You can't hear me?
Oh wait, maybe my speakers are.
Yeah. So what can X be? That's the question. Okay, so that's for the first homework. So actually, it's a small typo that changes the whole thing and makes the problem trivial. But I didn't notice it. But it's a bit strange that no one else also noticed it. So yeah, so that or maybe I'll keep this here. Yeah. So and then yeah. Apart from that, let's start with the lecture for today. So last time we were doing some matrix concentration. Today we will do a slightly different kind of concentration, which is with a single matrix. And in doing so, we'll also look at a general technique that that we'll use for proving some concentration type results, and also a technique which is sort of useful in many other contexts as well. So the question that I'm going to ask is something like this. So yes, so there are many ways to motivate this particular question. I'm going to take one possible approach. So So the random matrix subject is very general. It arises everywhere in a lot of different places. I'm going to just look at one application and to motivate. So the kind of thing I want is something like this. So suppose we have this weird kind of coding, or not weird, but a slightly different real encoding problem. So here's a sort of an analog coding problem. So what is the situation? So what you have is that your message. So you will get a message, which will be a vector in n dimensions, and you will have an encoder. Let's say a linear thing. So which will map x to ax, where a is some m cross n, where m will be some function of n. Okay. So it's a linear encoder. So now you have a new vector, and then this encoded vector, this is called y. So the encoded vector, so encoded vector ax is transmitted along a channel, which introduces some noise. Transmitted along a channel, which introduces noise. So what happens that the received vector is some z, which is ax. So this is equal to y, and this is some ax plus some error vector. Let me call it e. E is also in R to the n. So this is the received vector. Okay. And now somehow there has to be a decoder which maps somehow z to dz, and what we want, which should be in Rn. So what we want is to minimize. So minimize dz minus x. So you want to decode back the correct vector, and the error is measured in 2 now. And of course, one might expect how well we can do with this will depend upon how much error was added. So, but we want to compare it against the L1 norm of the error vector. Okay. So the intuition for this is that the adversary. So this is sort of like a yeah, it's like some kind of a continuous generalization of the situation in the discrete setting where you were allowed to, the adversary is only allowed to manipulate only a fixed number of symbols. So the model here is that the adversary can, so it costs the adversary something to perturb each entry by a certain number. So a given cost to the adversary, so the adversary's cost for perturbing each entry is proportional to the perturbation. So sort of assumption is this. Okay. So this is what we want to do. So for a given cost to the adversary, we want to minimize our error in the decoder. Okay. So suppose I asked you this question: what's a possible solution? Yeah, and also minimize this. So also minimize minimize this and m. So we don't want to blow up the vector too much. So m by n to increase the dimension. That's like saying that if I want to transmit n quantities, I don't want to transfer too many more than n. Okay. So by the way I have written it, so that's what I was going to ask. The way I have written it, there's a very trivial solution which with m equal to n. Can you tell me what the solution is? So like a possible solution which will give a good, decent bound for this. So consider we just think of it like an engineering term. So suppose you have this signal, you want to transmit it over a channel. There is some adversary with a bounded power. What can you do to just swamp out the adversary? Like just increase the power by a lot in your signal, right? So just instead of transmitting x, transmit something like some m times t times x for a very large number t, right? And then the decoding is just divide the signal by t. Okay, so suppose so trivial solution is ax is just t times x, t in r plus, and dz is just z by t, and then this dz minus x, the 2 norm is x tx plus e by t minus t, the 2 norm, which is e, the 2 norm by t, which is less than e1, the 1 norm by t. So you get that this by just increasing the power, you get a 1 over t decrease. So you can make t very large, and so these are clearly not so. But yeah, so can get. But this is clearly not a practical or even reasonable solution. But this is clearly not reasonable because this is looks like saying that you now are transmitting with a lot of power, right? I mean, so that's not what you want to do. So what you want to put in is another power constraint. So this is not a, but just increasing power is not a reasonable solution. So let's put another power constraint. So you put a power constraint, which is the total powers that you transmit. So the L2 squared power that you transmit is not more than the actual power of the signal. So you have to choose A such that this is true, and then you want to minimize this. Okay. So now, what is the best one can hope for this problem? So
what was the, can you just go back? So we are saying, how did we bound the part of AX? So this is saying that the first
you're not allowed to increase it to now.
right. So this is saying that the singular value should be at most 1.
Yeah, the singular value of
That's-
A, whatever this matrix is. So you have to. So the whole question is not to design this matrix A. The design we made initially was just a diagonal matrix with T on the diagonals. But that we are not allowed because we are not allowed to have singular value more than 1. Let's say any constant can be similar, but yeah, let's say 1. So if you can get a constant, you just divide. But yeah, but now with this, yeah, so what can we hope for? So suppose there's no error. Well, I mean, that's not quite, or a very small error, like somehow like the decoder could get very close to. What should be our sort of scaling between these two? Or the other, maybe another direction of thinking is, like suppose we are doing this linear decoding. What's the best, like what's the reasonable decoding procedure? How should you decode? So you have A, you have received this Z. A is like M is suppose much larger than N. You have received Z. How should you try to find this X tilde or this DZ basically? So you've received some vector Z, which is like AX plus E for some X.
So find the one which is like closest to.
Yeah. So the thing to do is to reasonable, so possible decoding strategy. In some sense, you can justify that this is probably the only decoding strategy. Is given Z, find the closest what? Closest what?
Closest possible.
Yeah. So where? So Z is AX plus E for some X. X is in R to the N.
closest thing in range space of A.
Yeah, right. So yes, so the closest vector is Z tilde in range of A. And clearly you cannot distinguish between different vectors in range of A, right? Because if I just see something in the range of A, I don't know whether that was because the adversary put in some error or because that's what was sent. Right. So if I see something in the range, I cannot decode any errors, right? Because that might just be what the person sent. Right? So yeah, so in the range I'm limited, but if I'm outside the range, my best bet is to go to the closest vector in the range. Okay. Right. And so yeah, so Z is Z is argmin. Okay, let me not write this one. So Z is the closest vector in the range. But we also want to decode. So then how do we decode? So Z is in.
Once you've found out such a Z tilde, then you can apply inverse of A.
Yeah, so on the range A is invertible, right? So on the range I can invert A. So so for every y in range A, there is a unique y tilde defined to, which is defined to be A inverse. Yeah, so this is just linear algebra such that A. So A is sort of inverted. Yeah. So usually this so inverse on the range, right? So usually the inverse does not make sense because the matrix is rectangular, but on the range it makes sense. Okay, right. So now, so this should be our answer. So our answer should be, so our final answer, x tilde would be the arc. So dz will be x tilde defined to be the arc min of ax minus ax tilde minus minus what am I saying? Sorry. So we just A inverse of z tilde where z tilde is arc min y in range A, what y in range A set P1 norm. Yeah, so the close, yeah, so the closest has to be in one norm, right? So I should have said in the, because the error was introduced in the one norm. So here it's one. Okay, so now what is the error of this? So now can we get some kind of bound on z on x tilde minus on dz minus x? So first, let's try to see how far. So in terms of E, let's say. So question one. So how far is z tilde from z in terms of E? Let's say. Can you say something about that? So notice that z was how far from the range of A? At most the norm of E, right? Right. So we know there exists y equal to ax in range A such that z minus y, the one norm, is equal to E, the one norm. Right? So this means, so we must have z minus z tilde, the one norm, is at most, right? Because z tilde is the minimizer of this quantity. Right? So this certainly is there. So z minus z tilde is not very large. Yes, it's at most E1. Okay. So we have z tilde, and now we do an A inverse on this. So yeah, so that is one thing. Yeah. So how much bigger can that be? So our goal is to estimate this dz minus x. We have shown that the z tilde is at most E, norm E1 away from z. How much away is it from AX?
Like if singular values of A are bounded, then singular values of A inverse will also be bounded in some way, right?
No, but right now I'm just asking for this in terms of E. So this right now the question of values of A won't come up. Yeah, it will come up soon, but not right now. So this again you can put something. So how big can this Z tilde minus AX be? Well, let us see. So
This is 2E, right?
yeah, exactly. Yeah. So because this is just the same thing as Z tilde minus Z plus Z minus AX, which is by triangular inequality. Right? And both of them, so this one is at most E1, this is equal to E1, so this is less than 2 times. Right? Okay, so now what we have is, so therefore, we have that A minus A, or rather AX tilde minus AX, the one norm is at most 2 times E1, right? Or because this is because the Z tilde was just AX tilde, where X tilde is the decoding of Z. So, so that is just saying that the A X tilde minus X, the one norm, is less than 2. Now can we put a bound on X tilde minus X, the 2 norm? So we are multiplying this whole thing by A inverse, right? So X tilde minus X, the 2 norm, is is equal to A inverse times A X tilde minus X. So remember, this A inverse is really the inverse of A on its range. Okay. So we are applying it to a vector on which it is defined, because by definition the range of A. 2, right, which is less than, therefore the operator norm, the 1 to 2 operator norm of A inverse times uh, this one norm of this, which is less than A inverse. So 1 to 2, the 2 times that times E1. So what is this? Where where for a matrix M, M1 to 2 is supremum over all V. The norm of V is at most one norm of V of the 2 norm of. So going from vectors which are of L1 norm 1, how far can you go into now? That's just by definition, and therefore, so by just this definition, you get this. So the upshot of all of this is that if we have A such that AX is less than X, right? So this is a thing we have. Then the above decoding process achieves dx minus, or rather uh, dax plus e minus x, the 2 norms divided by the 1 norm of e1 is less than um, a inverse, it's a inverse of 1 to 2 e1. Sorry, there's no e1, it's 2 times this. Okay, so yeah. And in general, so suppose we had a matrix. So in general, suppose we had an M cross N matrix such that the operator norm of matrix B such that B 2 to 2 is less than C. Then we can get so M cross N so M B such that then we can get then we can get a decoding process. So this is fine. B with some given 2 to 2 now. Then we can get a decoding process D such and a matrix A. What will be this A? It will just be B divided by the 2 norm. 2 to 2 norm of B. So 2 to 2 norm is the usual. Such that D AX plus E minus X over X over Z is less than the 2 to 2 norm of B times the B inverse 1 to 2. So this is sort of the important quantity. So the question is, how small can B 2 to 2 times B inverse 1 to 2 be for M cross N matrix? So this is the this is the defining the real geometric question. So this question answers the coding problem as well. So this is what you want to do. So we want to construct matrices where for which this number, the product of the operator norm multiplied by the 1 to 2 operator norm of the inverse is as small as possible. Okay. So any questions? So by the way, note that this does not change by scaling. That was the point of getting to this form. If you just scale B by C, this product does not change. Why is that? It's a trivial thing, but still. Yes. Why is that scaling by a constant does not change this product?
If you scale B, then B inverse gets scaled by the reciprocal, right? The norm of.
Yes. Okay. Yeah. So right. So that's what it is. And another way of thinking about this same problem is in terms of sections. So what is this B doing? So or maybe I'll come to that later. No, yeah. So let's. So what is this? So let's just think about what these things are doing now. So B is a matrix. It has some 2 to 2 norm. It's a M cross N matrix. So basically, what it is saying is that it's looking at a n-dimensional subspace in a larger dimensional space of dimension m. Right? So m is bigger than equal to n, and what this B is doing is taking a vector space R to the n and move and like putting it in, like embedding it somehow inside a largest vector space. Okay, and this B inverse is the inverse thing. It takes a vector from the space and goes back to R to the n. Okay, so suppose that B was actually just a rotation, like it was actually just so B was just some kind of a unitary matrix. It was actually just taking some orthogonal n orthonormal n vectors in R to the m and mapping the standard basis of R to the n into those vectors. Then B would just be a rotation, and this B inverse would be the opposite rotation. Right? Except that this B, the 2 to 2 norm, because it's a rotation, this will be 1, just because everything is moving by 1. And now the question is how much can this, what can this B inverse be? So yeah, so basically what we're going into is that we're going into a space. In this space, so we want to see how like what is the ratio between the 1 and 2 norms, right? So so let's just so a slightly different view. So just a vector space view. To consider the case where B is an orthonormal, B is orthonormal, B has orthonormal columns. So then it's just rotating. So they're not exactly rotations because they're like working on a smaller dimensional space. Right? Rotations, rotating a copy of R to the m sitting in R to the n sitting inside R to the n into a different space. So that they will preserve 2 norms. So they preserve 2 norms. Of vectors. So, but then this B inverse of 1 to 2 is just so you have to think a little bit about this. It's just the minimum over of x1 divided by x2 for x in range of t.
Other way around, right?
No, not the way. That's important. So it's B inverse from 1 to 2, and that's maybe you're right. So it's how. So I set small, right? So let me just check. So I set it. I want this number to be small. Yeah. So yeah. So B inverse is. Let's just do this calculation to just instead of doing it fast. So what is this? So this is by definition this is equal to max of x in the range of B inverse x, the 2 norm divided by x, the 1 norm. Yeah, so it's the inverse of the thing. That's what it is. Yeah. So yeah. So but what is this? So this is yeah. So So this is max over x in R to the n of y r to the n. So this is Yeah, or rather, this is x1, x2, because B inverse the rotation. So that so it preserves two numbers. And this is equal to 1 over what I wrote, 1 over the min. So what I want is I want this min to be as large as possible. So how large can this min be?
Root n.
Root m, because we're sitting in m dimensions. So yes, it could be as big as, so yes. So the question is, so could potentially be as large as root m. So so the so the question is that with m equals to theta m, can we get min x in range b, x not equal to 0, x1 by x2 to actually be omega root m. And if we could, then that would have implied the other solution. That would have implied this b also. So yeah, so the final thing comes. So these such things are called. So this is called a like a Euclidean section of L1. So why is it called a Euclidean section? Because what does this mean? So so this means that in range B, which is of dimension theta m, and which is subspace of R to the m of dimension theta m, we have, what do we have? So we have that the L1 norm is certainly always less than root m times x2. This is just true trivial. This is just Cauchy Shor's or something. But we also have that this inequality is almost tight up to a constant factor. Usually the difference between these two sides can be pretty high. But so the crucial thing is that on this space up to constant factors, x1 over x2 is equal to uh, it does not vary between 1 and root n. It actually is about root. So such questions were solved by Goritsky. So this is like saying that this thing. So the general question here is, inside a space, vector space with some equipped with some norm, how large a copy of another vector space with a different norm is sitting there. Right? So and this is like saying that inside L1, R to the m with L1, there is sitting an Euclid, like a space of just slightly smaller dimension, in which the L1 norm looks almost like L2. So this is like these Doritsky theorems. So this is like the simplest case. So this is perhaps the simplest case. and and so what the idea is that so what is this saying, that inside R to the m with L1 sits a subspace. So we haven't proved it, but this is what we prove, that such a thing exists. Such a subspace of dimension theta m, where L1 and L2 are essentially similar. That's why it's called a Euclidean section, because inside L1 you have found inside a vector space with the L1 norm, you have found a section, like a subspace, on which the L1 norm looks like an L2 norm. So that's why it's called Euclidean section. Yeah. So if you can find a Euclidean section, you can solve it. So the question now is, how do we find such these? This so far we are just so the question is, how do we find these sections? Such a B. So basically what you would want is, so what is such a B? So basically we'll want something like B222 should be small, and so so we want this to be about 1/2. So let's see. C1, C2 constants. So that's what. Yeah. So how do we find such a B? So any guesses about how we find such a B or such a space? So, so any guesses? I mean, yeah. So, I mean, to say something.
Random entries.
Yeah, but yes, okay, good. So, what kind of random matrix?
Uh,
So let's concentrate on this condition first. Like we want a random. So let's say we want to do a random matrix. How do we get the first condition? So what should the random? So the idea is maybe a random D works. So let's look at the easy. So the easy part first. So what should the random matrix look like, at least for the first condition to have some hope of holding? So don't worry about the one too much. Just says we want some constant here.
Say like each entry will be basically 0 or 1.
Okay, 0, 1. Let's say, yeah. So symmetric might be better. So let's think of the, yeah. So let's think of +1 -1. So you're saying something like that Bij is equal to +-1 with property half independently.
Yes.
Okay, so does this, what will its norm be like?
I think we need to scale also, right?
So let's just look at expectations, right? So let's look at, suppose this is our B, and we look, let's fix so U in Rn such that the operator, the true norm of U is 1. What is the expectation of, let's say, Bu, the true norm square? Let's just compute it. So this is expectation of what? So it's summation with linearity it becomes b j square, j goes from what? So this is the jth coordinate of bu. But what is the jth coordinate of bu? That is just j equal to 1 to n summation b j I going from 1 to n ui square expectation. Okay. And now what? What is this expectation? So let's compute it. So what would be the, so
This would be like norm of U.
yeah, so let's see, so what would be the expansion of this and what will survive?
The terms are independent, then cross term will vanish, and
Yeah, the cross terms will vanish. So this will become I equal to 1 to n bji ui squared.
square.
Yeah, so this will bji will just become 1 ui squared. And so what does this become?
So this is equal to m.
Equal to
1 equal to m, right?
Yeah, this is equal to m. So yeah, yeah, it makes sense that you basically, what you have to do is to make sure each column of B is a unit vector, because you want sort of B to look like a rotation matrix, right? That was the whole point. So this doesn't work, but if I put a 1 over m here, then things are better. At least the expectations sort of look nice. Right? Okay, so yeah, so let's first ask. So let's suppose that this is the thing we want to work with. So now the goal is to prove that with this choice, let's say this B 2 to 2 norm is less than C with reasonable probability, with, let's say, probability bigger than 1/4 at least. For some constancy. So right now we've just said that for any fixed vector u, the expectation is 1. Now we want to say the operator norm is doesn't, which is the same thing as bu 2 norm square is less than C for every unit vector u in R to the n. It has to be the case. We have just shown so far that the expectation for any fixed u is 1. What we want is that for every u, this has to be the case. So can we use a union bound, because we only want probability 1/4? Can we just use a union bound?
No, but this is
Sorry.
there are infinite possible U's. Right?
Yes, there is, yes. So for any one u, yeah. So we do have. So from this calculation here, we do get that that probability u in our n u the 2 norm is, we have that the probability that the 2 norm um, is bigger than t is less than 1 over t square for every t. Um, but we can't take a union bond. But we can't take a union bond overall. Overall, there are uncountably many of them. And this inequality also is not uncountably many. And this inequality also that I wrote down is not necessarily the tightest one that we have. But the bigger issue seems to be this, that there are uncountably many U's. Not uncountably. Yeah. Yeah, uncountably would not be. I mean, even if the fact that there are infinitely many is already a problem. Okay, so there are two issues. One is that the also star is not quite that. Star is not the best. So yeah, that is true. So this I will leave you to maybe solve this. But the point is that yes, but this can be tightened. This can be made into a holding leg bound. So we'll do that maybe later. Or maybe maybe just do the holding leg bound. Using the fact that for every fixed u, for any fixed u, each entry of bu is sub-Gaussian, is sub-Gaussian, and also different entries of bu are independent. So yeah. And sub-Gaussian with what parameter? With what is the parameter? So from hoping, sorry.
So the sigma square, the
Yeah. So it's so if I remember, so it's like with parameter that is like theta 1 over m. Well, so with not theta 1 over m.
Right.
It's yeah. So each entry of b. Mm, 1 over m, 1 over root m, and with so u squared 1 over m square root. Yeah. So it's 1 over, yeah, that was
yeah,
correct.
1 by m.
Yes, 1 over m. So in the sense that the expectation of bu I, one sec. lambda is less than e to the power c lambda square by m for some constant c, for some fixed constant c. Just make sure that I'm not using a square root. Right, so this is 1 over. Yeah, okay, I think that's correct. Yeah, yeah, that's fine. Okay, so each one of them is sub-Gaussian with this term. So yeah, so from this and an argument very similar to the one that was there in the question 4 of the previous homework, except that the way it was written, it became trivial. You have to put a 2 here to make it non-trivial. But yeah, but after doing this same argument, you get from this that so from this and an argument similar to the to problem 4 in our homework 1. Okay, we get that. The probability that BU minus 2 now minus 1 minus is greater than C plus T is less than X minus C1 C2 T squared. Yeah. C1 and C2 are forever T positive. Positive constants. Just once again, I think I messed up again. So it should be M. Okay, so it is exponentially decaying in M for any good. So in particular the probability that there is some yeah, so I can just fix a T here. So let me say that some C is bigger than minus C to M. The crucial thing is this M. But still, even with this, we can't take a union bound, right? Maybe I'll keep this. Even with this, I can't take a union bound over it because still there are infinitely many U's. Although the probability of error is much smaller, still there are infinitely many. Okay, so what do I do now? So this is the crucial thing. So the main idea is this idea of instead of taking a union bound over infinitely many u's, we just want to do it over finitely many u, and somehow from those conclude the result about all u's. So this is where the idea of epsilon net comes in. So let me slide this, but still we need to take a union bound over, take a union bound over infinitely many u's. All we can do is take exponentially many of them, exponentially in m. So okay, so this is where the idea of an epsilon net comes in. So what is an epsilon net? So what we will do is find a finite collection of u, norm of u less than equal to 1, such that every, this expression called as f epsilon, such that every u with norm u less than equal to 1 is close, let's say epsilon close, to some element. Okay. Why does this help? Let's see. So our goal, so the question is, why does this help? So suppose, yeah, so here is how it helps. So so suppose f epsilon is something like this. Suppose f epsilon is a finite set such that the following holds: one, that for every u such that operator norm of u is at most 1, equal, let's, yeah, that's 1, this so here the operator norm is equal to 1. There it is. Um, there exists um, there exists v in f epsilon such that u minus v, the up to norm, is at most epsilon. And the second thing is that on this everything is fine. That on these guys, bu2 is less than c for every u. Less than c. So there is a c. So for every v in f. So on every v in the finite set, bv is small now, and for every u, which may not be in the finite set, there is some v in the finite set such that u minus v is the length. So that is that f epsilon is up in, this is just in that it's epsilon net. Second thing is on the epsilon net, bv is good. It is not increasing the norm too much. So why will that already imply the full result? This is because suppose that the actual 2 norm of b is some m. So this exists, right? By just analysis, compactness arguments, there is some m so that it is the operator norm of b. We don't know what it is right now. But suppose if we have 1 and 2. So with 1 and 2, what do we have? We get, so we get it for any that, so we get the following. Take u such that the operator norm, the vector norm of u, the two norm is at most 1, then there exists v in f epsilon such that u minus v is less than epsilon. Now look at b, the two norm. What is this? This is just b of v, p of v plus u minus v, right? Which is by triangular inequality. And by the way, this is less than m, right? Sorry, this is bigger than m. M is bigger than b, right? Because m is the operator, which is equal to this. So um, take any use. Any use. This is less than bv plus bu minus v. Now bv we know is at most c, so this is from 2, and this is less than m times the norm of u minus 2, u minus v. Yeah, the 2 norm. This is because b, the 2 to 2 norm is equal to m. So therefore we get that for which in turn is less than c plus m epsilon, because u minus v is less than epsilon. So we see that bu is less than c plus m epsilon for every u such that u is less than equal to 1. But what does that mean? So right now there's no probability going on. So I'm saying it, suppose there's a matrix B such that it has this norm on, so it has this bounded norm on f epsilon, and epsilon is a epsilon net. Then we already have from those two just this fact that bu is at most c plus m epsilon for every u such that norm of u is at most. But if I take a supremum, this part doesn't depend upon you. This part depends upon you. And if I take a supremum as u over u of this, with u being less than 1, 2 norm, what is this side? Right? So, but what is this now? What is the
M.
left hand side? Sorry?
M, right? M.
Yeah, it's exactly equal to m. So this means that m times 1 minus epsilon is at most c, which means that m is less than c over 1 minus epsilon, assuming that epsilon is same. So the upshot of this is that if I can take a finite set, which is epsilon net for small enough epsilon, and not very small epsilon, anything less than 1 works, let's say epsilon equal to half, and if I prove a bound, if I get that the operator norm just on the epsilon net is at most c, then the operator norm on the whole set is at most c by 1 minus epsilon. Right? Okay. So the lemma is that let f epsilon be an epsilon net for the unit ball for x such that if b satisfies bv less than c for every v in f epsilon, then the operator norm of b. So there's no probability. Any b works. Is at most c over 1 epsilon. But now we have, yes, now we come back to probability. Now it's clear, right? So if there is an epsilon net, then all we have to do is to prove 2 for the epsilon net. And so we have to just take a union bound over everything in the epsilon net. So let's try to find such an epsilon net. Okay, so how would we find such an epsilon net? So now the question is, how does one find FE? And once we have done that, then it will be easy, right? So then you just use this star, take the union bound over f epsilon, use that to get 2, and then you're done. So that part I won't do. But the question I want to do is how does one find f epsilon? So one is this concentration. Yeah. So how do we find this thing? So, so this is again another simple but very useful idea. It works in several settings. So I'll do one example here. There will be another kind of example of an epsilon net using a slightly different argument in the homework. And hopefully you'll see one or two more using this method that I'll show in the class on coding theory. But still, like there is, so this should be intuitive. So like how would you, if I asked you to find an epsilon net for a set, what is the obvious thing to do? Pick a point, and then what? So at least one point has to be there, let's say. Then what do you do? How do you pick the second point?
So pick a point and discard all elements within epsilon
Yes. Okay.
distance. Then pick another point, and then just keep doing it till you
Okay.
come.
Yes. Good. Yes. So the suggested so we don't have to find it. We just have to show existence or show existence. So maybe a process is that pick. No, so suppose we have picked so far points p1 to pk. To pick the next point, we pick a point. So if necessary, we pick a point that is um, that is at least that is whose distance to all the previous point is greater than epsilon. Why can we always find such a point? Well, if we can't find such a point, then we are done, right? Then we have our epsilon net, because if every point in the set, right? So f epsilon, yes. So pick a point in the ball. So if you can't, so if the process, if we can't if you can't find such a point, then we are done. The question is, how many times will this process work? So how many times will this process work? How do we get that?
Sorry, actually our starting space is infinite, no? So how are we doing this? Like, it will go
Sorry?
on forever, right? Our starting space is infinite space, right? Infinite dimension.
It's not infinite dimensional space, it's a finite dimensional space. It's some
Finite dimension, yeah, but on the ball we are okay, okay.
Yeah, so say epsilon net for the L2 ball, and the way we are going to pick it is we pick a point, and yeah, and then yeah, so and then so we pick, first point we just pick arbitrary. Second point has to be at least epsilon away from, and in general, any point is epsilon away from all the other points. Okay, so whenever we pick a point, we make sure that it's epsilon away from all the other previous points that we have picked. And when we cannot do this, find such a point, we are done. The question is, how many such points can we find?
It should be something like volume of the ball divided by.
Yes, why should it be that? Yeah, so that's the question. So let's just do this carefully. So the balls can intersect, right? I mean, like it can be like if I draw the epsilon balls around these points, that can intersect. So what are the balls? So I cannot just add volumes because the total volume of all the balls of radius epsilon around these points can be much bigger than the volume of the balls. The same volume might be counted several times. So we want to ensure that the volumes that we are counting are sort of disjoint. Yes, you're on the right track. So how should we do this? So epsilon doesn't work. So what will work? So the invariant that we are maintaining is that p minus q, the 2 norm, is greater than epsilon for every 2 points, 2 distinct points in our collection.
But we can say that balls of radius epsilon by 2 are disjoint.
Yeah, exactly. Yeah,
Because
yeah, because they so the balls of radius epsilon by 2 around distinct points yes cannot intersect. Right, so okay, that is one point. And now what? There's one more observation we need. So what do these balls have to cover, or how what is the total volume of these balls? So all these points are in the ball, right?
so all these points are inside the ball of radius 1 plus epsilon.
Yes. So no, all the points are inside the ball. So now second, since P in S implies that norm P is less than 1, the ball of radius epsilon by 2 around P lies in this set, which is all those vectors whose norm is at most 1 plus epsilon by 2. Right? Because the total, so if something is in the ball of radius epsilon by 2 around P, its distance from P is at most epsilon by 2. P has distance from 0 at most 1. So the total distance, the distance of this point from 1, from 0 can be at most 1 plus epsilon by 2, just by triangulating for it. So this means that, so 1 and 2 give that the total volume of the union of the ball of around p of radius epsilon by 2 p in S is equal to the sum over p in S volume of the ball p around p of epsilon by 2, right? And this whole thing is also less than the volume of the ball around 0 of radius 1 plus epsilon by 2. Okay, so this is what we have. Now how do we, from this, how do we get a bond on the size of S?
Yeah, so the left hand side is the size of the set into volume of
All
epsilon
of
by
these balls have the same volume on the left hand side, right? Because they're just translations of the ball of radius epsilon by 2, right? So this is equal to S times the size of the ball around 0 of epsilon by 2. Okay, and now what? So this is translated because the balls are just translations of these points. And so we get that S times the ball, well, this is the volume. So we get that S times the volume of the ball 0 epsilon by 2 is at most the volume of the ball 0 1 plus epsilon by 2, and therefore S is less than the volume of the ball of around 0 of radius 1 by epsilon by 2 divided by the volume of the ball of 0 1 epsilon by 2. Yeah, okay, but what now? Is
this like some constant into 1 plus epsilon by 2 power.
this it, or what is the volume of ball scale? How does the volume of ball in dimension m scale?
Yeah. A power n, right? There's a power.
Yes. So now so we get this is less than 2 over epsilon plus 1. Okay, which is less than 3 over epsilon to the n. We never actually used L2, by the way, in this epsilon argument. It works for any LP now. We check that. The ball, of course, changes, but this we didn't use what the volume of the ball was. We only used how the volume of the ball scales. Okay. So yeah. So that's it. So but yeah. So now the point is that this is only exponential in m. So it's like m log some constant. So epsilon you can take, for example, 1/2 for this, for the problem we are trying to solve. And so this will be 6 to the m. And now the 6 to the m competes against something that's again exponential in m. So for a large enough constant c, you do get that bb is less than c in operating 2 now for every vector. So yes, you so get it with high probability. The operator number b is constant with this. So what is left? So as I said earlier, so this along with 1 establishes the easy part, that the easy part that the B has chosen probability positive. In fact, you'll get something better than that. Okay. So, so the other part is somewhat trickier, but has you can use it. You can prove it using similar similar similar. So basically, so now you have to look at B inverse. Now B inverse doesn't have independent entries. B has independent entries, but you can sort of try to write the norm of B in terms of B inverse. So now you have to be looking at the minimum norm of a vector. So what is the smallest norm of, or yeah, so. What's the smallest norm that a particular vector can have? So if I take B and apply it on a vector V, what's the smallest norm that BV can have? Right? If it was 0, then B would be non-invertible, but that's not going to happen because you're looking at the range. So now we have to bound the lower side. So it's often called a hard edge, but this is slightly different. So you're looking at V, you will be looking at a vector V, and you would want to say that for every vector V, BV is bounded away from 0. And that will give you a bound on B inverse, and that will in fact reuse the bound that you have on B, the Pareto norm of B also. So 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 the B inverse can be handled by estimating, by giving a high probability and this is a lower bound. So far you're looking at upper bounds. Now we have to do a lower bound on BV. Let's say greater than equal to or equal to. So how this can happen? This I will leave to you on BV1. Yeah. So the opposite side. This is not a tricky thing. You can just writing down the expression for B inverse 1 to 2, you can get this. We already actually in fact did this calculation above just here. Where was it? Yeah, it's the same calculation that we did here. And then yeah, so and then you'll do and then you'll have to do and then slightly different epsilon net argument again. So I'll encourage you to try to do this. Now the epsilon net that you have to use will not just be a constant. You'll actually have to you'll have to be finer. But yeah, but that's it. So yeah, so this is not doing class. This is for you to do yourself. Okay, so this will be the end of this part of the class. I think next class onwards we will be looking at Prahlad will be starting, and that will be on multiplicative weight upgrades and algorithmic framework. Yeah. So any questions for today?